Hi, I'm Benjamin, Director of Engineering at Firebolt, and today I'm going to show you how multi-threaded execution works in our query engine. Alright, let me get that example query on the board. In this query, we're trying to get the sum of revenue from all our sales in the US and Germany. Now, the hardware you're running on in Firebolt has multiple CPU cores. What this means is that your CPU has multiple independent worker units that can all do processing in parallel. Of course, we want to return the query result as quickly as possible. What this means is we need to figure out how to map the data flowing through the SQL query onto different CPU cores. At the storage level, Firebolt organizes its data into tablets. So the sales table might have 2 tablets stored on S3. Each of these tablets internally is organized into a set of independent chunks. So you could imagine that basically each tablet here has 4 chunks that can be decompressed and read independently. Now, let's figure out how to execute this query in a multi-threaded fashion. What Firebolt is going to do is that depending on the number of CPU cores you have, we set up that many independent processing lanes that can all work on the query in parallel. In our example here, we have 4 CPU cores, so we will set up 4 of these processing lanes. Each of these processing lanes is a chain of relational operators. So, at the very start, we have the table scan itself. After reading the data, we have to filter it. This is where we look for all of the sales that either happen in the US or Germany. And at the very end, we do an aggregation. We get the sum of the revenue. Now, we connect each of these lanes. What's going to happen in Firebolt is that each CPU core now gets pinned onto one of these processing lanes. This means that they can all work independently. As example, CPU core 1 might get pinned onto this first lane. CPU core 3 gets pinned on this third lane. And then they just independently go through all of the steps within this chain of operators. When I do a scan task, I'll pick one of these independent chunks of records in our storage layer. The scan will then decompress that chunk and pass it on to the filter. In parallel, another core could be working on another chunk of rows from the same tablet. So in this case, we have 8 chunks of rows, which will be evenly distributed across the different cores. After the scan, we passed small chunks of data of a few thousand rows through these processing lanes. So the scan produces, say, 4,000 rows, passes it to the filter, which checks which of the sales from the base table are in the US and Germany, and finally, whichever rows pass through that filter are being aggregated, again, in a completely thread-local fashion. After the aggregation, each thread now has a local sum of revenues. This means that at the very end, we need to combine the thread local state of all of these different aggregation processors and get them into one final sum of revenue. This is called an aggregate merge phase and happens after the completely thread local aggregation. With this design, Firebolt can scale to many CPU cores, which has minimal contention between the work of different cores. Each core pins itself onto a processing lane, picks a morsel of work from the source operator and then starts pushing it upwards through its local processing lane. For some operations like aggregations and joins, there's some coordination required between threads. However, this coordination is again done in a fully multi-threaded fashion. Alright, let's look at this in an example. Here, I loaded TPCH at scale factor 100. TPCH is an industry standard benchmark, and scale factor 100 means that there's about 100 gigabytes of data in this dataset. I also started 3 engines here. One, Firebolt Small, is the smallest engine we have in Firebolt. I then also started a medium and a large engine. In Firebolt, going to these bigger engines means you're actually scaling up. You can scale into multiple dimensions, so you could also add more nodes to the engine here. But in our case, it's just a single node on this engine and we scale up. Perfect. Let's start running this query. This is quite close to what you've seen in the previous example. We get the sum over a price where L return flag is set to either R or N. When we run this on the small engine, we can see it takes about 4.75 seconds and scanned 11 gigabytes. Now, let's scale up. A medium engine in Firebolt costs twice as much, but it also has twice as much processing power. And you can already see that while the query took more than 4 seconds before, we now take pretty much exactly half the time, 2.35 seconds. If we scale further to a large engine, we can see that the result now comes back in about 1.3 seconds. So as I move from small to medium, the engine will consume twice as many FBU hours. But it also means you can scale up perfectly and get your query results twice as fast. The same thing happens as you go from medium to large. So in other words, the jump from small to large gives you a 4x performance boost. What this actually means is that if you look at the price for your individual query, nothing really changes. You throw more resources at the problem, and it means that your query finishes quicker. As Firebolt has consumption-based pricing, and when your engine is not running, nothing actually changes about the cost of this individual query. In the previous example, we've seen that we set up these independent processing lanes. We saw this for the simple example query here, where we do a scan, a filter, and an aggregation. However, we also mentioned that for some operators, you need to do coordination work between the different threads. Let's see what happens if we move to a much more complicated query. In this case, I loaded TPCH query 18. What's happening here is that we're doing a join between line item orders and customers. Line item and orders are the biggest tables in TPCH. We also see we have some subqueries and a rather large aggregation and order by at the end. So this is a pretty heavy query. Let's see what happens as we scale up Firebolt on this query. We start by running on small, and this takes a while to complete. We can see that the query returned results after about 16 seconds. In that time, it scanned 12.83 gigabytes of data. Let's now run this on the medium engine. If it scaled perfectly, we would expect the query to finish in about 8 seconds. And indeed, after 7.78 seconds, this query finishes. So again, we throw twice as much hardware at this query, and it finishes twice as fast. Finally, let's move to the large engine in Firebolt. Here, if its Firebolt scales perfectly, we would expect the query response after about 4 seconds. And indeed, after about 4.7 seconds, the query returns. So, you can see that even for this very complex query with multiple joins and aggregations, as you scale up your engine, Firebolt becomes faster and faster. And this is all because of what I've shown you earlier. Firebolt setting up these independent processing lanes to keep all cores busy at all time helps us to scale up effectively. If you want to try this out yourself, click on the link in the description and sign up for Firebolt and get $200 of free credits. Thanks for watching and see you next time.